Welcome back to the Chemistry 209 Masterclass series. This series of lectures is intended to highlight the key concepts of introductory spectroscopy and structure. This lecture, Masterclass 1, discusses the inception of quantum mechanics and its connection with spectroscopy. In Masterclass 0, we define spectroscopy as the branch of science concerned with the interaction between light and matter. We will be mostly concerned with the absorption and emission of light by matter, although in our section on Raman spectroscopy we will spend a little time discussing a third process, light scattering. Absorption is the process by which a low-energy atom or molecule is excited to a higher energy by absorbing light energy. The process of emission is the opposite of light absorption. When emission occurs, an excited atom or molecule relaxes to a lower energy by emitting light. Normally we discuss absorption and emission in terms of energy levels or states. For example, an atom can be excited from a low energy state to a high energy state by absorption of light. We find that atoms and molecules do not absorb or emit light at all frequencies or wavelengths. Instead, we find that only very specific wavelengths of light are absorbed or emitted, and that the patterns of absorbed and emitted light are unique to each type of atom and molecule. Developing an understanding of why this is the case is one of the main goals of Chemistry 209. When we measure the absorption or emission spectrum of a molecule or atom, we are actually measuring the energy differences between various states or energy levels. These transitions obey the law of conservation of energy. That is to say, when an atom or molecule absorbs light energy, the total energy of the atom or molecule must necessarily increase to compensate for the loss of electromagnetic energy. For atomic systems, energy levels arise due to the various motions of electrons. For molecules, there are energy levels produced by electronic motion, as well as rotational and vibrational energy levels that arise due to the relative motion of nuclei. We will also see that there are molecular energy levels associated with the relative orientation of nuclear spin magnetic moments, but we will wait for a few lectures before we delve into the concept of nuclear spin. A key question that we will address over the course of the next two lectures is, what are these energy levels and where do they come from? Our first strong evidence for the existence of the quantum nature of light and matter was provided by Max Planck's study of blackbody radiation. Blackbody radiation is the name given to the phenomenon whereby a solid object emits light whose intensity distribution as a function of wavelength is independent of the nature of the hot material. Blackbody radiation depends only on an object's temperature. For example, for matter at 300 Kelvin, we find that the blackbody radiation distribution peaks in the infrared region of the spectrum, whereas a material at 3000 Kelvin that glows red hot has a distribution that peaks in the red region of the electromagnetic spectrum. We can use our knowledge of blackbody radiation to estimate the temperatures of stars. The red color of Alpha Orionis, also known as Betelgeuse, tells us that its surface temperature is around 3500 Kelvin. Beta Orionis, also known as Rigel, on the other hand, is blue, which tells us that its surface temperature is approximately 15,000 degrees Kelvin. Before Max Planck's work on blackbody radiation, our best classical theory could reproduce the low-energy end of the blackbody radiation intensity distribution, but predicted infinite light intensity in the high-energy regions of the spectrum. Of course, in a finite universe, there is no such thing as infinite energy. This failure of classical theory became known as the ultraviolet catastrophe. Max Planck showed that the observed blackbody radiation distributions were modeled nearly perfectly with a relationship that has now become known as Planck's law. The critical aspect of Planck's derivation was the assumption that energy is emitted in finite increments. Planck showed that these energy increments, which became known as quanta, depend linearly on the frequency of the emitted light. The linear scaling factor that Planck found is now known as Planck's constant, and it is a fundamental physical constant that we will use often in Chemistry 209. Not long after Max Planck reported his findings on blackbody radiation, Albert Einstein turned his attention to a seemingly unrelated phenomenon known as the photoelectric effect. The photoelectric effect is the phenomenon whereby electrons are ejected from the surface of a material when the surface is illuminated. The key observations of the photoelectric effect are: that there is no time lag between the arrival of light and the emission of photoelectrons, that the number of photoelectrons increases with light intensity but that their kinetic energy is unaffected, that the photoelectron kinetic energy increases with light frequency but is independent of light intensity, and that each material has a characteristic frequency of light below which no photoelectrons are emitted regardless of the light intensity. Despite the fact that we know light exhibits wave-like properties such as diffraction and refraction, the observations of the photoelectric effect are completely inconsistent with light being a wave. We know from classical physics that the energy of a wave is proportional to the square of the wave amplitude, or here intensity. Thus, classical physics would predict that as we increase the light intensity, more energy should be deposited into the material, and the ejected electrons should fly away with a higher kinetic energy. This, of course, is not observed. More interesting still, if we plot the kinetic energies of the ejected electrons as a function of the light frequency, we find a straight line with a slope that is equal to Planck's constant. In other words, light is quantized. Today, we refer to the tiny energy increments of light as photons. So, Max Planck has taught us that quanta of energy are absorbed and emitted from matter, and Albert Einstein showed us that light must consist of tiny quanta of energy. Einstein's special theory of relativity also taught us that E equals mc squared, or more correctly, E squared equals mc squared plus pc squared. Thus, a further implication of Planck and Einstein's results, as recognized by Arthur Compton, is that photons must behave as particles that are subject to conservation of energy and momentum, and that the linear momentum of a photon must be wavelength dependent. The ability of photons to exhibit properties of both waves and particles is known as wave-particle duality. To see the connection between the quantization of light and spectroscopy, we need to backtrack a little bit. Nearly 100 years before Planck, Einstein, and Compton discovered the quantum nature of light, Joseph von Fraunhofer built an instrument called a spectroscope so that he could observe the solar spectrum. The principle of the instrument was simple. Fraunhofer passed sunlight through a glass prism and observed the relative intensities of the dispersed colors. In the mid-1800s, Gustav Kirchhoff and Robert Bunsen used a spectroscope to observe the emission spectra of atoms in high-temperature flames. Kirchhoff and Bunsen showed that each type of atom had a unique emission spectrum, which could be used as a spectral fingerprint for analytical determinations. Of course, at the time, nobody knew why atoms exhibited spectra that were unique to each element. The first step en route to understanding atomic spectra occurred in the mid-1880s when Johann Jacob Balmer empirically developed an equation that reproduced the visible emission spectrum of atomic hydrogen. Not long after Balmer reported his formula, Johannes Rydberg showed that Balmer's formula could be generalized to not only account for Balmer's series, which incidentally was measured by Ångström, but that the atomic hydrogen emission spectra in the infrared and far ultraviolet could also be modeled. Rydberg's rather simple formula employed spectral indices and a constant, now known as the Rydberg constant, and it reproduced the emission wavelengths of atomic hydrogen exactly. Although Rydberg's formulation yields perfect agreement with the experimentally determined atomic hydrogen emission lines, it does not provide any fundamental physical explanation for why the spectra are as they are. The situation remained this way for another 25 years. In 1913, Niels Bohr developed a theory in an attempt to explain atomic spectroscopy. Bohr's theory borrowed from Planck and Einstein's idea of energy quantization and from Rutherford's erroneous idea that electrons move in circular orbits around atomic nuclei. Bohr circumvented the errors introduced by Rutherford's theory by ignoring the fact that in Rutherford's model, atoms will collapse because electrons will lose electromagnetic energy and spiral into the nucleus. Instead, Bohr assumed that electrons were in a stationary state with a quantized angular speed. He also introduced the correspondence principle, which in a nutshell says that as system size increases, quantum results must agree with the results of classical theory. Realizing that the hydrogen atom is dominated by the interaction between the positively charged nucleus and the negatively charged electron, Bohr modeled the system with a Coulomb potential to describe the electrostatic attraction. Including his quantization and steady-state assumptions yielded an energy level equation wherein quantum states were described in terms of an index, now known as a quantum number, and a collection of fundamental physical constants which reproduced the Rydberg constant exactly. Moreover, Bohr found that the angular momentum of the electron was an integer multiple of Planck's reduced constant. Thus, Niels Bohr showed that hydrogen atomic spectra obeyed the laws of conservation of energy and conservation of momentum, since absorbed or emitted light must carry the energy and angular momentum associated with a transition between two quantized energy levels. For the first time, there was a physical explanation for atomic spectra. Bohr's theory was a huge leap forward towards an understanding of the quantum world. His explanation of the hydrogen atomic spectrum could be generalized for all one-electron systems, which meant that scientists could now exactly predict the atomic spectra for these species. Bohr's theory also allows us to calculate the size of atoms in different quantum states, and from this we see that if atomic hydrogen occupies the n equals 1000 excited state, its diameter is approximately the same as the diameter of a human hair. Despite the successes of Bohr's theory, his model was only accurate for one-electron systems. Since most of the atoms and molecules that we are interested in have more than one electron, this is a dead end, so there must still be something missing in our description. The key to unlocking the shortcoming in Bohr's theory was provided by Louis de Broglie, who took inspiration from Compton's research on the momentum of photons. In his 1924 thesis, de Broglie asked, since light can be described as a wave with the characteristics of a particle, shouldn't matter, which is made up of particles, also possess wave characteristics? De Broglie then went on to show that matter can be described as probability waves with wavelengths that are inversely proportional to the particle momentum. Note that the constant of proportionality in de Broglie's equation is Planck's constant. The concept of matter waves whose properties are determined probabilistically seems very strange on first thought, since this goes against most of what we experience in the large-scale world that we live in. For very small systems, like atomic or subatomic particles, this behavior is, however, the norm, and it has been proven time and again experimentally. In our next lecture, we will discuss how this dual particle wave-like nature of matter results in quantized energy levels and electron orbitals in atoms and molecules. See you next time.